Thermal expansion is the tendency of matter to change in shape, area, and volume in response to a change in temperature. Through heat transfer, temperature is a monotonic function of the average molecular kinetic energy of a substance. When a substance is heated, the kinetic energy of its molecules increases. Thus, the molecules begin moving more and usually maintain a greater average separation. Materials which contract with increasing temperature are unusual. This effect is limited in size, and only occurs within limited temperature ranges. The degree of expansion divided by the change in temperature is called the material's coefficient of thermal expansion and generally varies with temperature. Overview: predicting expansion. If an equation of state is available, it can be used to predict the values of the thermal expansion at all the required temperatures and pressures, along with many other state functions. Contraction effects. A number of materials contract on heating within certain temperature ranges. This is usually called negative thermal expansion, rather than thermal contraction. For example, the coefficient of thermal expansion of water drops to zero as it is cooled to 3.983 degrees Celsius and then becomes negative below this temperature. This means that water has a maximum density at this temperature, and this leads to bodies of water maintaining this temperature at the lower depths during extended periods of sub-zero weather. Also, fairly pure silicon has a negative coefficient of thermal expansion for temperatures between about 18 and 120 Kelvin. Factors affecting thermal expansion. Unlike gases or liquids, solid materials tend to keep the shape when undergoing thermal expansion. Thermal expansion generally decreases with increasing bond energy, which also has an effect on the melting point of solids. So, high melting point materials are more likely to have lower thermal expansion. In general, liquids expand slightly more than solids. The thermal expansion of glasses is higher compared to that of crystals. At the glass transition temperature, rearrangements that occur in an amorphous material lead to characteristic discontinuities of coefficient of thermal expansion at specific heat. These discontinuities allow detection of the glass transition temperature where a supercooled liquid transforms to a glass. Absorption or desorption of water can change the size of many common materials. Many organic materials change size much more due to this effect than they do to thermal expansion. Common plastics exposed to water can, in the long term, expand by many %. Expansion in liquids. Theoretically, the coefficient of linear expansion can be found from the coefficient of volumetric expansion. However, for liquids, alpha is calculated through the experimental determination of alpha v. Apparent and absolute expansion. When measuring the expansion of a liquid, the measurement must account for the expansion of the container as well. For example, a flask that has been constructed with a long narrow stem filled with enough liquid that the stem itself is partially filled, when placed in a heat bath, will initially show the column of liquid in the stem to drop, followed by the immediate increase of the column until the flask liquid heat bath system has thermalized. The initial observation of the column of liquid dropping is not due to an initial contraction of the liquid, but rather the expansion of the flask as it contacts the heat bath first. Soon after, the liquid in the flask is heated by the flask itself and begins to expand. Since liquids typically have a greater expansion over solids, the liquid in the flask eventually exceeds that of the flask, causing the column of liquid in the flask to rise. A direct measurement of the height of the liquid E-column is a measurement of the apparent expansion of the liquid. The absolute expansion of the liquid is the apparent expansion corrected for the expansion of the containing vessel. Examples and applications. The expansion and contraction of materials must be considered when designing large structures. When using taper chain to measure distances for land surveys, when designing molds for casting hot material, and in other engineering applications when large changes in dimension due to temperature are expected. Thermal expansion is also used in mechanical applications to fit parts over one another, e.g., a bushing can be fitted over a shaft by making its inner diameter slightly smaller than the diameter of the shaft, then heating it until it fits over the shaft, and allowing it to cool after it has been pushed over the shaft, thus achieving a shrink fit. Induction shrink fitting is a common industrial method to preheat metal components between 150 degrees Celsius and 300 degrees Celsius, thereby causing them to expand and allow for the insertion or removal of another component. There exist some alloys with a very small linear expansion coefficient, used in applications that demand very small changes in physical dimension over a range of temperatures. One of these is Inv36, with alpha approximately equal to 0.6 times 10⁻⁶ K-1. These alloys are useful in aerospace applications where wide temperature swings may occur. Pulling JIS apparatus is used to determine the linear expansion of a metallic rod in the laboratory. The apparatus consists of a metal cylinder closed at both ends. It is provided with an inlet and outlet for the steam. The steam for heating the rod is supplied by a boiler which is connected by a rubber tube to the inlet. The center of the cylinder contains a hole to insert a thermometer. The rod under investigation is enclosed in a steam jacket. One of its ends is free, but the other end is pressed against a fixed screw. The position of the rod is determined by a micrometer screw gauge's ferrometer. The control of thermal expansion in brittle materials is a key concern for a wide range of reasons. For example, both glass and ceramics are brittle, and uneven temperature causes uneven expansion, which again causes thermal stress, and this might lead to fracture. Ceramics need to be joined or work in consort with a wide range of materials, and therefore their expansion must be matched to the application. Because glazes need to be firmly attached to the underlying porcelain, the thermal expansion must be tuned to fit the body so that crazing or shivering do not occur. Good example of products whose thermal expansion is the key to the success are Corningware and the spark plug. The thermal expansion of ceramic bodies can be controlled by firing to create crystalline species that will influence the overall expansion of the material in the desired direction. In addition, or instead, the formulation of the body can employ materials delivering particles of the desired expansion to the matrix. The thermal expansion of glazes is controlled by the chemical composition and the firing schedule to which they were subjected. In most cases, there are complex issues involved in controlling body and glaze expansion. Adjusting for thermal expansion must be done with an eye to other properties that will be affected. Generally, trade-offs are required. Thermal expansion can have a noticeable effect in gasoline stored in above-ground storage tanks, which can cause gasoline pumps to dispense gasoline, which may be more compressed than gasoline held in underground storage tanks in the wintertime, or less compressed than gasoline held in underground storage tanks in the summertime. Heat-induced expansion has to be taken into account in most areas of engineering. A few examples are: metal-framed windows need rubber spaces, rubber tires. Metal hot water heating pipes should not be used in long straight lengths. Large structures such as railways and bridges need expansion joints in the structures to avoid sun kink. One of the reasons for the poor performance of cold car engines is that parts have inefficiently large spacings until the normal operating temperature is achieved. A gridiron pendulum uses an arrangement of different metals to maintain a more temperature-stable pendulum length. A power line on a hot day is droopy, but on a cold day it is tight. This is because the metals expand under heat. Expansion joints that absorb the thermal expansion in a piping system. Precision engineering nearly always requires the engineer to pay attention to the thermal expansion of the product. For example, when using a scanning electron microscope, even small changes in temperature such as 1 degree can cause a sample to change its position relative to the focus point. Thermometers are another application of thermal expansion. Most contain a liquid which is constrained to flow in only one direction due to changes in volume brought about by changes in temperature. A bimetal mechanical thermometer uses a bimetallic strip and bends due to the differing thermal expansion of the two metals. Metal pipes made of different materials are heated by passing steam through them. While each pipe is being tested, one end is securely fixed and the other rests on a rotating shaft, the motion of which is indicated with a pointer. The linear expansion of the different metals is compared qualitatively and the coefficient of linear thermal expansion is calculated.